So let's talk about heat. So heat is the transfer of thermal energy between a system and a surrounding. That transfer is caused by a difference in temperature. Temperature is a measure of the thermal energy that a sample has. So you could think of temperature as being like the balance in your account. How much money is in your account? And then heat is the transfer of money either into your account or out of your account. Okay? So the way it works with heat is it always flows from a higher temperature to a lower temperature. So this is just like a ball will always roll down a hill. Why is that? Well, it's going from higher potential energy to lower potential energy. And that is how things work in nature. They're always going to lower energy. So that heat will flow until the two objects reach the same temperature. If you take some water, some warm water, and you put ice cubes in it and you wait, the warm water is going to become colder, the ice cubes are going to melt and become warmer, and at some point they will be at the same temperature. The heat will not continue to transfer. You will not have the formerly warm water now become ice cubes and the formerly cold ice cubes become hot water. That doesn't happen. It's just going to go until it reaches a level where they're both the same. So if a system absorbs heat, then its temperature is going to go up. That increase in temperature will be proportional to how much heat went into the system, right? So we could say that the heat is equal to a constant times the change in temperature. More heat goes into the system, the change in temperature is going to be bigger. This constant, the proportionality constant, is called the heat capacity. And that's going to have units of joules per degree Celsius or joules per Kelvin. So heat capacity is the heat required to change the temperature of a system by 1 degree. Well, if your system, maybe your system is, pot of water, you're going to make spaghetti. You need to increase the temperature of the water, right? If you have a small pot of water or a big stock pot of water, and you want the water to go from room temperature to boiling, it's going to take more energy for the bigger amount of water, right? That just makes sense. Well, the heat capacity is just how much energy to change the temperature of that particular system. So then the water in your small pot would have a different heat capacity than the water in your big pot. And in fact, like everything is going to have its own unique heat capacity, and you take some of the water out of the big pot and now the heat capacities change, and it's like, well, this isn't much of a constant, is it? Right? Because it depends on the mass, the size of the object. So heat capacity, what we were just talking about, is an extensive property. It depends on the size of the object. More water, you're going to have a larger heat capacity, you're going to need more heat to change the temperature. So we have a similar concept. It's called specific heat capacity. That's a capital C with an S after it. And this is an intensive property. It's the intrinsic capacity of a substance to absorb heat. So how much heat this thing absorbs is going to depend on how big it is and also what it's made out of. But because the heat capacity does not depend on its mass, the heat capacity of the specific heat capacity of a small thing of water and a big thing of water is the same number. So the specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of that substance by 1 degree. So 1 gram of water in the small pot, 1 gram of water in the big pot, those are the same. They're going to have the same specific heat capacity. So the units for that are going to be joules per gram degrees Celsius. We can also talk about a molar heat capacity, and that's the amount of heat needed to change the temperature of 1 mole of a substance by 1 degree, and that would be joules per mole to degrees Celsius. We don't use that as much, but both of these are intensive properties. They do not depend on how much stuff there is. So here's our equation this is like the main equation for this chapter. This relates heat, mass, specific heat capacity, and change in temperature. Q equals mc delta T. Some people remember that as Q equals MCAT, because this kind of looks like an A, MCAT. So Q is the heat in joules, M is the mass in grams, this is the specific heat capacity in joules per gram degrees Celsius, and then the temperature change is in degrees Celsius. And all these units are going to work out. We've got grams times joules per gram degrees Celsius times degrees Celsius. The grams cancel out and the degrees cancel out, leaving us with joules. This is a short list of some specific heat capacities. There's a few elements here, there's a couple of compounds, and then there's different materials, glass, granite, sand. And so these are the specific heat capacities, and no, we're not going to memorize any of these. Okay? We're not going to memorize them. But over here, the metals have relatively small heat capacities, right? Aluminum's a bit higher at 0.9. But then when we look at ethanol, which is alcohol, and water's specific heat capacity is 4.18. That is really big compared to like 0.128, right? And then glass, granite, sand, these are back down between iron and aluminum, but all very much less than water. Water has a very high specific heat capacity. Because of its high specific heat capacity, water can absorb a lot of energy and only change in temperature a little bit. So this has a huge effect on our climate and our local environment. So here we have a picture of the San Francisco Bridge. So San Francisco is on a peninsula. It's surrounded by the ocean on one side and the San Francisco Bay on the other side. It's literally 3 sides water, right? All of that water in that area keeps the temperature regulated. The temperature does not get as warm during the day, and it does not get as cold during the night, because the heat for our planet comes from the sun, right? So the sun beats down during the day, and it hits the water, and the water absorbs this heat energy, and it warms up. But it takes a lot of energy to warm it up, and there's a heck of a lot of water there, right? So the water in the bay or the ocean warms up a little tiny bit, and then when the air cools down as the sun sets, well, the heat is going to go in the opposite direction, because now the water's warmer than the air. So heat is going to be transferred back to the air. And so that keeps the air from getting as cold as it does here. So San Francisco might be like 68 degrees Fahrenheit in the summer, whereas Fresno's more likely to be 100, right? If you've ever been to San Francisco, you know, I swear it seems like it's colder there in the summer than it is in the winter. It's very weird, right? Yeah. And so people make, I think, a lot of money selling sweatshirts right there at the Fisherman's Wharf, because the tourists come in and it's California, right? We're not expecting it to be cold. And they're shivering and, yeah, I'll buy a $20 sweatshirt, sure. So water is commonly used as a coolant because it can absorb a lot of heat and remove it from mechanical parts that we don't want to get too hot. So in your car engine, there is a system of coolant that flows through the engine, because as those mechanical parts move, there's friction and it generates a lot of heat. And to help that heat get away from the engine parts, your car has a pump that circulates the water through the engine. It goes through the engine, it gets hot, it comes back out to the radiator where it has a lot of surface area, and then it can let that heat out into the surroundings. Any questions? I just think this is kind of a weird problem, but here it is. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. There's a much easier way to figure out if this is gold. Find the density. Well, it's hard to find the volume of a rock. No, it isn't. Graduate a cylinder with some water in it, put the rock in the water, see how much the water goes up, put the rock on a scale, density, bang, you're done. But then that doesn't help us learn how to calculate these things, so we're stuck. Okay, we have 4.7 grams, we have 25 degrees Celsius, we have 57 degrees Celsius, we have 57.2 joules. And what are we trying to find? We are trying to find the specific heat capacity. So this is a case where we have to use an equation. And the equation is Q equals MC delta T. So Q equals MC sub S delta T. Okay, so let's pull these numbers out and find out what they are. We have 4.7 grams. Well, that's the mass, right? So I'm going to call that M. And then we have 57.2 joules. What should we call that?
No, we're looking for heat capacity.
Yeah. No.
What's the CS mean again?
That's the specific heat capacity.
There you go.
That's what we're looking for, though.
Oh, so it's your Q.
It's Q. Yeah, so this is Q. It's the amount of heat. There's no Q in heat, but H got used up a lot of other places. And then we've got two temperatures, right? We have 25 degrees Celsius, and we've got 57 degrees Celsius. Well, looking at the equation, this has delta T. So delta T is going to be the final temperature minus the initial. So which one of these is the initial temperature? 25. And the final is the 57. Because it says it changes from 25 to 57. So it's not going to be just specified for you, but the words will indicate. So we can calculate delta T. It's the final temperature, 57 degrees Celsius, minus the initial is 25. So change in temperature can be positive or negative. It'll be negative if the system is getting colder. It'll be positive if it's getting warmer. So 32 degrees.
What is the capacity? We don't need to change the Kelvin, we leave it at Celsius?
Great question, because we just got done with the gases chapter and everything was Kelvin, right? Here, we usually keep it in Celsius. Yeah. So I'm trying to find the specific heat capacity, so I'm going to rearrange my equation. And again, if you need help with that, please come and talk to me during lab, and I will show you. I've got several different ways to help you remember how to do this. I'm dividing both sides by m and delta t. So now I can plug my numbers in with their units. 57.2 joules divided by the mass, 4.7 grams, and the change in temperature, 32 degrees Celsius. And here we're dividing by two numbers that are multiplied, so again, you need to be careful on your calculator. So 57.2, what most people do is they'll divide and open the parentheses, 4.7 times 32, close the parentheses, equals 0.3803. So the mass only had 2 sig figs and the temperature only had 2. So we're limited to 2 sig figs there. And the units are going to be joules over gram, degrees Celsius. None of those are going to cancel out. So the answer to that is the specific heat capacity of this rock is 0.38 joules per gram degrees Celsius. But the big question is it gold? We need to look at the heat capacity of gold. And you don't have that in your head, you go to a table and you look it up. Well, the heat capacity of gold is 0.128. So it's not gold. The 0.38 is close to copper. This does not prove that the metal is copper or the rock is copper, but it would be a suggestion that possibly could be. So is the rock gold? No. Any questions? Let's do another one. A lot less words here. A 55-gram aluminum block, initially at 27.5 degrees Celsius, absorbs 725 joules of heat. What is the final temperature of the aluminum? So we've got 27.5, we've got 725 joules, we've got 55 grams, we have a question, or a command. It's a question this time. Final temperature. Well, this is one of those things where we've got a substance and the temperature's changing. And so that's, in this class, it's pretty much always going to be Q equals MC delta T. And knowing that I'm going to use that equation can help me identify these numbers. So 55.0 grams, it doesn't say that that's the mass, but I know that gram is a unit of mass. So I'm going to label that as mass. I have a temperature, 27.5 degrees Celsius. Well, that's not the changing temperature, is it? What is it? The initial temperature. It helps that they use the word initially. Absorbs 725 joules of heat. So 725 joules, that is going to be our Q. If it's absorbing energy, is that positive or negative? If my wallet absorbs money, it's positive, right? Okay. So we're trying to find the final temperature, and we look at this equation, and the final temperature is not just sitting there, is it? But we know that delta T is equal to T final minus T initial. We know what T initial is, so if we can calculate delta T, then we can find our final temperature because we know the initial temperature. This one's not as straightforward as the last one. So what I want to do is I want to calculate delta T. So rearranging the equation, I'm going to get delta T is equal to Q divided by M times the specific heat capacity. So Q is 725 joules. The mass is 55 grams. And, I don't know the specific heat capacity. Well, I just need to go look it up. So, on the exam over this material, these will be provided either in the question or somewhere convenient. So, for aluminum is 0.903. So, 0.903 joules per gram degrees Celsius. So, that guy's going to go down here. 0.903 joules per gram degrees Celsius. Again, dividing by two numbers multiplied, so be careful. 725 divided by open parentheses 55 times 0.903. Close the parentheses equals. I've got 3 sig figs in all of those, so 14.597 degrees Celsius. Let's look at those units real quick. So, I've got joules divided by grams, and then I have another fraction in the denominator. I'm dividing by a fraction. That is the same as upside downing, inverting the fraction and multiplying. So this is the same as times grams degrees Celsius per joule. The joules cancel, the grams cancel. I just graded worksheet 5, and I saw a lot of this, grams over grams per milliliter, canceling the milliliters and getting grams. Well, no, because that would be times milliliters over gram, and that's actually milliliters squared per gram, which is nonsense, right? So that's another reason why I don't recommend using the density equation, except if you're calculating the density. Let's avoid dividing by fractions whenever possible. Okay. So our units worked out, and I have my delta T. So delta T is our final T minus our initial. So then that means that the final temperature must be the change in temperature plus the initial temperature. So 14.597 degrees Celsius plus 27.5 degrees Celsius. Calculator says 42.097, and so we're going to call that 42.1 degrees Celsius. You can see how you might get this a little mixed up and maybe subtract instead of add. So think about it for a minute. If the block is absorbing heat, is it going to get warmer or colder? It's gonna get warmer, so we expect the final temperature to be higher. Here, our final temperature is higher than the initial temperature. So that's encouraging. Any questions? Makes me want to go to San Francisco.